Good. So, yeah, let's just get started. Few announcements. Exercise 3, it's due next week, next Monday, and there's a Q&A session with Balin today. For the exam, there's a reminder. Please register if you wish to take the exam. It's not close to the deadline for registration yet, but before you forget, right? So today is the penultimate lecture, and next week will be the final lecture. So last year we did something around exams and about the research group that we have at the University of Tübingen. So these were the final lecture materials last year. And also some Q&A and maybe some additional topics that you like. So this year again, I'd like to kind of get your feedback on what you wish to hear more. It could be, one of the plan was to kind of have this uncertainty estimation for foundation models, for example, but it didn't actually go into lecture 11. So maybe we can talk a little bit about that in the final lecture as well. Yeah, or if you have any questions to be answered that you like to get an answer for, then you can also send the questions. And let's get started with the main material of today's lecture. Last week, we talked about epistemic uncertainty. We talked about Bayesian machine learning based approaches where we kind of get a set of models that are all solving the training set nicely. And which are supposed to be kind of disagreeing or be diverse on out of distribution samples. And based on this property, you try to infer which samples are actually coming out of the distribution. Or we had a distance-based measure where you look into feature space and say if your distance of your test sample from the other samples in the training set, if this distance is far enough, then you can say this is OD. Let's talk about aleatoric uncertainty today. Again, aleatoric uncertainty is the kind of uncertainty that arises because there are multiple plausible answers. For predictive task of going from X to Y, if there are multiple possible Y given X, in other words, if P of Y given X has a variance, then there's an aleatoric uncertainty. We've seen multiple examples 2 lectures ago. So these are the top 2 rows are samples of low aleatoric uncertainty because the Py given X, the ground truth, is unimodal. But these are the cases where P of Y given X is multimodal and therefore have high aleatoric uncertainty. This typically also arises because the task is supposed to be single class classification, but eventually in the image, there are multiple classes. So depending on the annotator, they might come with different single labels for the image. Or there's some corruption or erasure of some features in general. Then there's uncertainty as well. In general, when there's an unobserved latent feature, for example here x2 in the left case, then the classes tend to get become overlapping, even if in reality they are not overlapping, if you observe the full set of features. So this is kind of the generative process for aleatoric uncertainty. Or maybe the task itself is by nature aleatoric. If given a single caption, there are multiple different plausible ways to generate an image. So in practice, the aleatoric uncertainty looks like you get the same kind of sample in your training set, but for the same kind of sample, you're going to get different labels from different labelers. In other words, you're going to get mixed supervision. It doesn't have to be the same X, but even for very similar X samples, you're going to get very different signals. So to kind of overfeed to the solution, then you have to learn a very, very wiggly and very complex function to fit to data. So there has to be some kind of trade-off between how overfitting you should be and how smooth you are, and still kind of allowing for a bit of aleatoric uncertainty. So there are two ingredients for modeling aleatoric uncertainty. One is architecture, and the other one is the loss function. So architecture-wise, you have to devise kind of model architecture which admits multiple plausible solutions, first of all. And in terms of loss, you have to use a loss function, which is encouraging the model to faithfully represent the true distribution of the outputs given the input. Okay, so let's take a look at the most basic task of classification. In classification, what people normally do is softmax with negative log likelihood. But now, let's say the P of y given x is multimodal, and you're going to see mixed supervision that's coming from the ground truth distribution of P of y given x. The question is whether the existing solution here, softmax with negative log likelihood, is it already solving the problem of aleatoric uncertainty? To get to the conclusion first, the answer is yes, and the reason is because that's a proper scoring rule. Okay, so let's take a look at this claim from the two perspectives. So one is architecture and the other one is loss function. So from the architectural point of view, since we have softmax, which is encoding all possible predictive distribution over the label space, we can say that architecture-wise, we are ready to model multiple possibilities, right? You can just spread your bets across different labels. In terms of the loss function, we are using negative log likelihood. And again, this is proper scoring rule, and therefore we say, yeah, this is actually modeling aleatoric uncertainty. So let's take a look at this claim in more detail. So in lecture 9, 2 lectures ago, we looked into proper scoring rule, but at the time we defined scoring rules for binary predictions, right? So C of x, for example, is a single number indicating your confidence for the positive prediction, and L is a binary event telling you whether the model is going to get the prediction right on this sample or not. Okay, and there the log probability scoring rule was basically log of C of x when L is equal to 1, and otherwise log of 1 minus C of x, right? And we show that this is actually identical to binary cross entropy, the negative log likelihood loss function. And so by solving the usual BCE, binary cross entropy loss, you're actually encouraging the model to make the right estimation of the predictive uncertainty, right? So the same applies here, right? For binary prediction, we know that it has to encode P of y given x correctly, because here P of y given x is essentially predicting the probability of y equals to 1, right? If you predict the probability for y equals to 1, then you automatically have the probability for y equals to 0 by taking 1 minus of that. So we have to extend the definition of proper scoring rule from binary case to discrete case in general. By discrete, what I mean is finite. So there's also infinite discrete, but what I mean here is more finite discrete. When there are multiple classes to select from, so you have a classification problem. The extension of proper scoring rule to actually any distribution is quite straightforward. If you remember from 2 lectures ago, scoring rule is just a function of a distribution Q and Y, where Y is the sample from some true distribution, and Q is your prediction of the distribution, basically. You can think of that as more like parameters for this distribution as well. Okay. Given that, right? Given that definition, it's not so hard to extend the scoring rule definition to discrete random variables as well. It's still a function, right? The properties of scoring function is also kind of straightforward to extend to discrete case. You say a scoring function is proper when the expected score under when the expectation is taken with the y, the sample distribution. This is maximized if and only if your prediction is equal to the true distribution p. Okay, so what does that mean in practice for classification problem? Let's try to match now a predicted categorical distribution, which is, for example, softmax output of a neural network. It's going to be c-dimensional, where c is the number of classes vector, which sums to 1. And let's say there's some true categorical distribution, p of y given x, where you can sample y and put the labels on each x. Your log probability scoring rule is defined as follows. It's basically summation over all possible classes, and yk is a one-hot vector indicating what's the label for this sample. Okay, and yeah, fk of x is basically kth entry of this prediction vector. You take the log of that, and then you multiply with this binary. So eventually what's happening here is you're just taking the log of the ground truth entry of the prediction vector, which is just an LL, right? No log likelihood. But this is log probability. The claim here is that the log probability scoring rule for discrete random variables is a proper scoring function. And this is left as an exercise to show that S defined this way is a proper scoring rule. In other words, if you take the expectation over y, that expression here, the expected score, is maximized if and only if all the predictions from your function fk of x for every k is actually the true probability of predicting of y equals to k for the given input x. So I won't prove it here, but I hope you try it. So far, is there any question or unclear bits? Okay. I mean, if there is any unclear bits afterwards, you can always ask. Now, what's the implication for aleatoric uncertainty? As I said, aleatoric uncertainty is the possibility of modeling the true p of y given x. And now we are saying that this is a proper scoring rule, which means that your predicted distribution q is equal to the true distribution p. And so if you use this function, and if there's a guarantee that you're minimizing this loss function sufficiently in average case, then we know that we are modeling the true p of y given x. And therefore, we have perfect aleatoric uncertainty estimation. So a common misconception with log likelihood loss is that it's actually encouraging the model to be overconfident. I hear that from some people from time to time, but the truth is not that, right? If there's a mixed supervision and actually the true label is coming from some multimodal distribution, then the cross entropy loss learns to model the true dispersion of the labels for every sample. Since people tend to not believe that still, so I made some toy case to kind of show this is the case. And here's a toy data set with two Gaussians with a bit of overlap near this x1 plus x2 equals to 0 line, right? So that's the decision boundary here. And around this region, you're going to see mixed supervision for training the model. Of course, here you're going to see more clear labels. Okay, so the question here is around these samples, what's going to be the predicted uncertainties or predicted distribution for each x? To make a reference point, we calculate the ground truth aleatoric uncertainty for every x, which is given by P of y equals to 0, which is again using Bayes' theorem. You can kind of flip the two. And then since we have full generative process, we know that these are Gaussians and coming from two different centroids, we can actually express everything here. And if we do that, then it's basically a likelihood ratio between the summation of the two distributions and the distribution corresponding to class note. Okay, so if you plot this, it looks like this. So this is only encoding the probability for y equals to 0 everywhere. So of course it's higher here and it's lower here. The question is whether if you train with this kind of data here, are we going to recover this kind of prediction for every x in the space? We train a model with the log likely loss, log scoring rule. And then this is actually the prediction of the model, right? So it's remarkably similar to the ground truth here. So it verifies that if you train with log likelihood, then you're actually recovering the true dispersion of the ground truth labels for every sample. And this is the plot for the difference. So green here means 0, and there are some errors where the samples are not there, right? Which is understandable. But still, in general, especially around this point, the dispersion is very precisely predicted. So as long as there are enough samples, we know that this loss function will recover the aleatoric uncertainty. So that was it for classification problem. Now let's take a look at the regression problem. Now the true distribution P of y given x is continuous. Okay, regression is still the problem of predicting y given x, but y for regression is now continuous variable. Okay, and the true distribution over the continuous space is now, rather than a single kind of point in the y space, but it's kind of distribution over y space. The most popular distribution that we assume for P of y given x is a normal distribution in regression, right? So you can think of P of y given x. You can assume that P of y given x is some density function parameterized by density function for the value y, which is parameterized by mu of x and sigma of x. Okay. I put I here just in case this whole thing is the y space is multidimensional, but you can think of this as just a 1D regression problem. In that case, you can just remove this I and think of that as sigma of x squared. So here, what is noticeable and what is quite different from normal regression problem is that I put x here for sigma. If you think of just linear regression, for example, you're assuming that there's noise, of course, for the observations, but you assume that the noise are independent of x. We call that homoscedastic regression problem. But now we say the noise level is actually dependent on the x. And this is heteroscedastic problem. If you think about aleatoric uncertainty, what matters for us is heteroscedastic regression problem. Because if the noise is always the same across the whole input space, then there's no point in estimating the aleatoric uncertainty, because the uncertainty is anyways going to be the same everywhere. Yeah, and if a quantity is always a constant, then you're not interested in the quantity anymore. So this is an example of heteroscedastic regression. So you have mu of x, of course, which is the true mean. But now the true variance is also a variable of x. And you have to model that using the samples from the distribution following n of mu and sigma squared. Another visualization which also has epistemic uncertainty in place. So this is kind of a visualization, which shows aleatoric and epistemic uncertainty together. So if there are a lot of samples, then you have lower epistemic uncertainty. But now with a lot of samples, you have greater dispersion of along the y-axis. And therefore you say, yeah, this is quite a bit of aleatoric uncertainty again. Some example application in computer vision. If you're trying to predict the depth of a scene, then you can also try to get pixel-wise depth, right? And depth is a continuous variable. And so there you can also try to have some kind of continuous uncertainty estimate for every different pixel. Yes.
If you go back on the slide, these are two different kinds of variance plotted depending on dataset size. But I don't get the epistemic part.
Okay, so I'm gonna explain a little bit more here. So these black dots are training data, right? And you're fitting a model here, right? And let's say the model is also giving you an estimate of epistemic uncertainty and aleatoric uncertainty together, right? And this is kind of an example estimation from this model. And this kind of makes sense because for the region where the training data is scarce, then you say, yeah, the model says, yeah, I have higher epistemic uncertainty here. Whereas for, even if there's a lot of training data because you have too much noise in the observation, you say, yeah, I have higher aleatoric uncertainty here.
So then each of the data clusters has multiple classes stacked in one place. Because if all this was a single class, then there wouldn't be any.
So yeah, sort of. But there's no notion of class here. This is a regression problem. So there's only y here. And the prediction target is kind of much more diverse here. It's a continuous variable. But, okay, makes sense. All right. So now the question is, we have seen that proper scoring is such a strong tool. So why not use that here for continuous distribution as well? Again, we can extend the definition without too much difficulty. We can say, the scoring rule is basically, again, a function of predicted distribution and the sample from the distribution. And it's proper if and only if the expected score given the true distribution for the sample is maximized if and only if the prediction your prediction is actually encoding the true distribution. So what does that mean in practice in regression? So yeah. I didn't hear the first part of it, sorry. So how does it apply here, right? So all I'm saying here is that this is another regression problem. Although, like, depending on your viewpoint, you can think of this as a multidimensional regression as well, because now you're predicting per pixel a continuous variable, right? And so you can think of this as kind of a regression in the space, very high dimensional space of all possible number of pixels. But still, this is a continuous regression problem. And so there you can also build some Gaussian model of the prediction and then try to fit this model to the data that you observe. If that's the case, then you can think of this still as one example of, like, one extreme example of regression problem. Okay. And here the uncertainty matters a lot as well, because depending on this is also kind of how to say, ill-posed problem. You never know what is the true answer, right? But just by observing several examples in the real world, you're trying to kind of extrapolate that observation to new kind of scenes. But of course, um, depending on, like, let's say there's a white scene, like whiteboard there, right? And there's inherent ambiguity whether the white here means if the color is really white, or somehow the board is really far away, but still you see always white colors because the depth is, the whole 3D space is colored white. And like one great example is when you have only white in the scene, then you never know what is the depth of the scene, right? And so in that case, you're going to have very high aleatoric uncertainty, because for the same white scene, you will see different ground truth depth if you're sampling sufficiently from the space. So that's a good typical case of ill-posed problem. And for these ill-posed problems, you're going to also see quite a bit of mixed supervision. And if you take care of that mixed supervision sufficiently well, using all the techniques like proper scoring rule, then you should be able to recover the true P of y given x again, and be able to tell, okay, for this image, I have seen so many cases with different depth, and so I would say I don't have confidence here to tell you what is the right depth. And that's going to be useful in practice. Yeah, I should have explained a bit more here, but sure. So coming back to continuous distribution, I just said proper scoring is the identical concept here. It's maximized if and only if the true distribution is predicted, is given to the scoring. And here I'm going to use log probability scoring rule again. And I'm going to argue that log probability is, again, a proper scoring rule. For continuous distribution, log probability is given by S of Q and Y is equal to the log of the density function of Y. Okay, so here we assume that it's a continuous distribution and it has a density function, and so you can take a log there, and yeah, it's going to be a proper scoring rule. Well, that's actually the exercise here. So what does it mean that this scoring rule is a proper scoring rule? It means that the expected value here, which is given by the expectation over y and log q of y, which is again represented by integral over p of y times log of q of y dy, right? This is maximal if and only if p is equal to q, okay, or q is equal to p. I'm not going to prove it here, but I wish you to try it by yourself. The hint is to use Jensen's inequality, which states that if you take the average of log of average, here average should be kind of with respect to some probability measure, actually. It has to sum to 1. If you take average of log of some function, that's smaller than log of average, okay? Okay, what does it look like for Gaussian assumption on the y distribution? Okay, we assume that P of y given x is y given mu of x and sigma squared of x times I, okay? So we are assuming isotropic Gaussian here. Yeah. If you like, you can also assume more degrees of freedom for the covariance matrix here, but for the sake of simplicity, I would say this is isotropic, but variant with respect to x. I think that's already a lot of complexity here, so I'll just live with that. And now the model is f of x, and f of x has two heads now. One head is predicting mu of x, and the other head is predicting sigma of x. Okay, so now the predicted distribution, predicted density over y is given by q of y given x, where you take the density value at y for the distribution parameterized by the f of x. Okay. Yeah, I hope everything is clear so far. Otherwise, I can always come back and explain again. So let's try to plug in the formula for Gaussian density function in the log probability scoring rule. So let's write down minus of the scoring rule, which is given by minus log of q of y given x. And q of y given x, if you can plug in the formula for the density. And if you remember correctly, then that's 1 over square root of 2 pi sigma squared times exponential of minus 1 over 2 sigma squared times the L2 norm between L2 distance between y and mu. Okay. Normally we don't care about this term here and we just throw it away. But now this term also depends on x, and that's kind of the objective that you have to also predict correctly. So we can't actually throw it away. And if you do all the cleanup here by removing log and x together and so on, then you end up with this formulation here. 1 over 2 sigma squared times y minus mu L2 norm squared plus 1 over 2 log of sigma squared plus some constant term. We don't care about constant term because this is independent of the optimization problem that we're going to solve. So again, here the problem is to predict mu hat and sigma hat correctly. So let's dissect this loss function in a bit more detail. So the first term here is telling you that you have to solve this L2 norm minimization problem, right, between y and mu. Well, that's normal. But now that's weighted by the factor 1 over 2 sigma squared. Okay, that tells me that we put less weight on the loss here, L2 loss here. So if sigma is high, right? When sigma is high, we know that the sample has higher uncertainty. And then we're going to have, it's 1 over that, so we're going to have less weight for that sample. So what this tells me is that if the model declares I find this sample too hard, then I'm going to put less weight on this loss function, loss value for that sample. So it's kind of giving the model to kind of a possibility to assign lower weight on really uncertain samples. But then there's a second term, right, which is there because if the model is given a chance to say, I don't want to solve this problem because it's so hard, right, then the model can, in principle, do that for every sample. Okay. That is not encouraged by this whole loss function because of this term here. Because if you say there's too much uncertainty for every sample, right? High sigma for every sample, then you're going to have to pay a lot of cost here because it's an increasing function of sigma. Although it's log, so it's the cost is a little bit less than it would have been if that was a linear function. But still, this is kind of a budget value for kind of assigning high uncertainty for truly confusing cases. Okay. So that kind of makes sense, but still I wish to kind of have a proof, an empirical proof that it actually works in practice. So again, I came up with a toy case here. The thick blue line here is the ground truth, and the band here is 1 sigma band around the true mu. So the width here is the true sigma here, okay? And this is heteroscedastic. And likewise, the samples show much more variance and much more mixed supervision towards the edge of the space, while for the center, you have more uniform prediction, uniform output distribution. And now, if you train with this loss function that we came up with in the previous slide, then this is the prediction, mu, and the predicted sigma here. Okay, so we see that we are almost very closely recovering the true distribution for every x. So this is good. So we covered categorical distribution and continuous distribution. What about more complex cases, right? Is there anything more complex than these two cases? Well, actually, continuous distribution is complex enough, but we'll also take a look at the cases where it's more extreme among the continuous distributions. Let's take a look at future prediction. If you think about future prediction, like it's a self-driving car and you wish to understand whether the pedestrian who's waiting for the light for the crossing, are they going to cross it or not, right? There's no single correct answer, or you probably don't want to put too much bet in single answer here. So there's a natural aleatoric uncertainty in future prediction. But the thing is, for predicting future in general, the space of possibilities is way too large. It's very high dimensional space. So yes, this is continuous still, but the dimensionality is way too huge. And also, you cannot possibly model this with single Gaussian as we did for regression problem now, because typically the future is multimodal. Depending on the internal state or some discrete states, you may show qualitatively different behaviors in the future. So you somehow need to encode some multimodal distribution in high dimensional space here. Or image painting as well is, well, actually a depth estimation that I just showed. That's another case of high dimensional prediction. So that also applies here. But also image painting is another hard example here, where you have to predict a bunch of pixels, like thousands or millions of pixels together. And you know, this is also multimodal because sometimes you wish to kind of introduce a new object altogether, and then from the pixel space point of view, you're introducing a dramatic shift from one possible patch to the other. So this is another multimodal kind of distribution. So again, common challenges here. There's aleatoric uncertainty. There's no single good answer. But it's kind of hard to estimate P of y given x with a single Gaussian because the set of possibilities is way too complex. It's either multimodal or high dimensional, or or both. So to address this, one possibility is to make use of mixture of Gaussian. Okay. In particular, I'm interested in mixture of Gaussian with fixed variance as the model for Q of y given x. Okay. So the difference from before is that before in regression problem we looked into Q of y given x is a single Gaussian, and now it's a mixture of Gaussian. And now it's composed of m different experts, I would say, and each expert is encoding the density function for different mu's. But sigma is kind of fixed for every expert here, let's say. So you know, like we're not looking to heteroscedastic regression here anymore. But that's fine because we are encoding the variance now with different centroids. So centroid here is the primary source of heteroscedasticity in the prediction problem. I hope that's clear. This is multimodal, and actually this is a universal approximator for any continuous function as sigma goes to 0. If you have taken some course in non-parametric statistics and so on, then you might have seen the results using, I forgot the name of this kernel estimation, kernel regression, some name there, and you can model any continuous density function with kernel density estimator. Does anyone know the name of this estimator? No? Okay. And there they say if you reduce the size of sigma according to, I remember, maybe a 1 over n number of samples or 1 over square root of n or something, then you're recovering the true density distribution arbitrarily well. So you don't need to know all these details. The only point that I'm making here is that I'm not sacrificing any freedom of modeling capacity here by saying we're going to model a mixture of Gaussians with a fixed variance. In fact, that's given epsilon, we can arbitrarily closely fit any continuous density function with an error, whatever that error means, is bound by epsilon. So although that's going to be, if epsilon is super small, then it will be super inefficient, but theoretically it's possible. So sure. Mm-hmm. Sure, yeah. So one way to think of that is, for example, here we are looking at heteroscedasticity, which is good. But let's say there's a second group of samples here, right? Which is kind of separate from the first line. So somehow the output y of x is multimodal, right? There's a, so for if you focus on this x here, there's a cluster of samples here for y. But let's say you also observe a cluster of samples here. Then if you assume a single Gaussian, it's kind of hard to model this. But yeah, if they have different variances, if you have sufficiently many experts in the mixture of Gaussian, then you can still model that by assigning more experts here and less experts here, for example. So we're kind of generalizing beyond the single Gaussian case here. Okay. And in terms of DNN, how you do it is by introducing some DNN trunk at the beginning, and then you're going to have different heads for the experts. Okay. And each of the experts will be predicting F1, F2. These are basically mu's for different centroids. And we are not modeling sigma anymore because it's constant anyways. So what's going to be the loss function here? So we talked about architecture, right? So what is the loss function that's going to be suitable here? And since we are still talking about continuous variable, and we already know that for continuous random variable, log scoring rule is still a proper scoring. So we're going to use log scoring rule again. And that looks like this here. So it's basically minus of log of the density, where the density is now the mixture of Gaussians. So it looks like log, sum, and density, basically. I wish to give you more insight into what this loss function is doing internally by expressing the loss value here in terms of the individual loss value, as if you are training individual experts separately, which is given by LM here. Okay, so I'm going to talk about that after a 5-minute break. So we wish to use the log probability, but before using it, I mean, you can use it as well, just trusting that it should work. But for me, it matters to really understand what the loss is doing. So I would say this is not really published in some paper. At least I haven't seen this published somewhere. Only through like my own curiosity and eagerness to really understand what's happening in terms of the gradient and so on. I did this kind of analysis several times actually across different projects. And then something crystallized out here. And this is kind of the results. So there are actually a lot of cases in machine learning when you have to put a log likelihood on top of some mixture. And this is one of such case. And whenever you have this kind of log of sum of something, you end up having a very similar pattern in terms of the individual supervision you're assigning to different experts in this ensemble, if you can call this ensemble. And this can be expressed in terms of the loss value if you had just that expert to train. Okay, so compared to that, how is the supervision different by using this log likelihood? So that's the question. And here's a full formulation to tell you that what this is doing is essentially some scaled version of this, where the scale is kind of funny. So let's go one by one here. So I wish to take the gradient for L expert to L here. So what I do is I take the derivative of the log likelihood loss with respect to one of the parameters of one of the experts. And you know, there's log upfront, so you can do chain rule, and you have this kind of expression here. You can see already that m kind of cancels out. And then, because of linearity, you can pull the derivative inside the summation. Let's plug in the qm of y given x. Remember, that's just you know, the density function for mth components. And now you do chain rule on x. So there's nothing really involved here. You just use chain rule over and over again. So for x, you have x here, but you derive the internal value here, right? And if you follow further, well, before following further, you can actually define this value here, right? As some weight term, WL. Because eventually this is just about L, right? Because M here is a dummy index. It's just the summation over all the experts. So it's kind of constant for every L. So in short, this is just WL, right? Some kind of weight you put on top of this value here. So this part is now W here, and this part survives, right? But you put log and x together, right? They cancel out, right? But instead of canceling them out, I revived them here because I wish to go back to the form of QL of y given x. Actually, x of that is basically QL of y given x. So what we have here is basically WL times derivative of minus log probability of QL. And that's actually the log likelihood loss for expert L separately. So eventually, right, this derivative of the original log likelihood is essentially just training that expert L with some weight multiplied in front of the usual training signal. So, right, so we have this relationship. Now the question is, what is the WL here? How is that defined? If you look closely at WL, that's again, yeah, that looks like this here. But if you look closely, you realize again that this part here is basically minus log of L, right? Is that right? Yeah? This is log of loss of L, sorry, loss of L. And this is loss of Lm, sorry, loss of M. So it's basically a softmax value over the loss values for different different experts. Very neat. Yeah, you could also write it as, instead of saying, yeah, the gradient looks like this, you can also say, actually, you can turn the log likelihood over the mixture of Gaussian into this simple summation over individual losses where you put some weight on top, but you're not training through this weight. You put stop grad to make sure that you're not training the parameters through this WL. So it's essentially the same, where WL is given by the softmax over minus logs. What does that actually mean, right? What does softmax over minus log means? Minus loss means? So if you plot Wm or WL over different experts M, then you're going to see different heights, different values here. Well, actually, they should sum up to 1, right? Because it's softmax value. Which one gets the highest weight, right? And the one with the highest weight is the one with the lowest loss, right? And the one with the lowest loss is essentially the expert who was the most correct, right? Because if you're correct, then you have lower loss value. So in other words, this weighting scheme is giving expert more weight if the expert is more correct. It's kind of counterintuitive because typically you wish to penalize the more wrong ones, right, than the more correct ones. But here you're actually penalizing, well, the fact that you're giving greater weight means you're also kind of trying to train it further, right? So if one of the experts is doing a very bad job at something, then you just give up on that and then find some other expert who's doing a better job and just train that one, okay? So if you think about the dynamics here, it's kind of promoting specialization among the experts. If at initialization, some of the experts are doing slightly better than the other experts for a certain problem, then you choose that expert to solve this problem. And you continue doing that. You reinforce this over iterations. And now, sigma is playing a role here as well. If you're familiar with the temperature concept for softmax, are you familiar with temperature for softmax? It's essentially a factor that you multiply in front of the value inside this x in softmax. So in this case, sigma is a temperature. And if your temperature is higher, then your softmax value will tend to be uniform. It's higher entropy, basically. And if the temperature is lower, then it tends to be more one-hot vector with lower entropy. So sigma here is kind of hyperparameter deciding how to assign weights. Okay, if sigma is very high, then regardless of who's right or wrong, you're still going to train every expert in the same way. In the most extreme case, when sigma is close to 0, then you're really going to pick one expert who's correct and then only train that one and just forget about everything else. So here, the special case when sigma is approaching 0 is called a k-diverse loss, where you are extremely promoting diversity rather than correctness, actually. You do not care whether every expert is correct or not. You just care if at least one of them is right. Okay? And the loss function, if you look closely, looks like this. So the WL is essentially now a one-hot vector like this. You only have one for the most correct expert. And it's going to look like this one-hot vector. And combined with the summation here, you can write it down as loss of L, where L is the argmax of WP. And actually, argmax of WP is exactly when the loss is minimal. So the loss value in this case is exactly min loss over the expert. So you're just training the minimum, right? This is kind of crazy because let's say for a given X, the set of experts are doing all kinds of weird answers. And let's say only one of them is correct and everything else is incorrect. Then you're still going to get loss equals to 0. And from the loss perspective, we are happy. If you train a model with this kind of loss function, what's going to happen is the model will diversify as much as it can because it's going to hedge the bet everywhere and just hope that one of them is right. And that's good enough, right? Because you're going to get 0 loss in that case. So you can think of this as, for example, like MNIST prediction, for example. Let's say this is an MNIST classification task and there are 10 experts. Then what the model will learn is to predict 0, 1, 2, 3, 4, 5, up to 9 with each expert. And that's going to give you 0 loss for every case. So it's kind of a very extreme case where there's potentially no training at all depending on how many experts there are. But still, we have a knob to turn, which is sigma here, between this very extreme diversification and kind of a uniform training of every expert here. And in between somewhere is kind of a sweet spot that's going to promote diversity to encode the heteroscedasticity of the problem, as well as the correctness of mu. Actually, this kind of log likelihood over mixture of Gaussian is not seen in many literature. As I said, I haven't seen such a formulation so much before, but the min loss comes out super frequently in literature. For example, here you see that this method called DiverseNet is using the minimum loss over experts. So C here is expert index. And you're just training the most correct experts. And if you do that, here's ours. And the task here is to in-paint the rest of the quadrants. And yeah, it predicts these diverse possibilities pretty well. Right. And this is another typical case of ill-posed problem. You only see the silhouette and you have to guess the 3D structure. And that tends to work well with the DiverseNet again. It also comes up in this kind of literature where mixture of density network is used. Here, it's not a classification problem, but still they're using regression target here, but the weight is given by whether index is indicating the arg mean over the loss value here. So it's the same kind of loss, mean loss. They call it winner takes all loss, but essentially this is the diversification loss. Okay, so far everything is clear, or okay? Okay, let's move on to representation learning. So we looked into discrete prediction task, continuous prediction, more complex multimodal prediction, right? And now let's talk about representation. Representation learning is still predicting some continuous variable, but instead of giving direct supervision for the continuous variable, we're only treating that as a latent variable where we do not have any observation. So what do I mean by that exactly? So let's say we wish to build a vector database, if everyone is familiar with the vector database. Let's say you wish to look for some legal documents, right? Then what you do is you featureize every legal document in a database in terms of feature vector. And at test time, let's say you have some search query or some new document, and you wish to find the most similar legal document in the database because you wish to kind of take a look at that. Then what you're going to do is you're going to featureize this query into the same space, and then you measure the distance in this vector database in terms of cosine distance or Euclidean distance, whatever you like. And then you're going to crawl the nearest neighbors in this vector database. So that's kind of how you use the representation learning. That's why you need it. How you train it is basically with using these pairs. There are different versions of training a representation, but this is the most popular one, right? So you try to, your goal is to estimate a mapping to Z from X, where Z is a latent variable, right? But for training this model, you do not get the labels for Z. You only get the labels for Y, which is given for every pair of samples, X node and X1 and X2. And the Y is only telling you whether these are similar or not. Okay. Again, there are different variants like telling you how similar as well, like Y could be a continuous variable, for example, or it could also be kind of relative. So if there's X1 and X2 and X2 and X3, you can also say, yeah, X1 and X2 are more similar than X2 and X3. So there are different variants, but essentially you are giving the model information whether given a two sample, are they same or not, or identical or not, or similar or not. And using that information, eventually you wish to train a Z, okay? It has to be inferred. I'm gonna talk about aleatoric uncertainty for this kind of representation learning. Why do we need that in the first place? So let's say, we also say this is an embedding space. We say representation space, embedding space, feature space interchangeably, okay? So f is a function that maps from the input to some feature space. And let's say 17 is mapped here and 47 is mapped here. Yeah, and if the new 47 comes, then we're going to map it there. 17 comes, then we're going to map it there. No problem at all. But the problem arises when there's a new sample which has some aleatoric uncertainty. Neither of these answers are good because you're still committing to one of these. And also this solution is not so great either because you're, I mean, every point in space has kind of meaning here, right? So there's no region in space which is reserved for, I'm kind of confused between 17 and 14, right? So that's also not super good. So what we do here is to introduce probabilistic distribution over the latent space. In this case, two mixture of Gaussian here. Okay, so here the problem statement again, to clarify it again, is to estimate the distribution P of Z given X. Instead of just a mapping from X to Z as before, we're interested in distribution P of Z given X. Ingredient is the same. We observe X1 and X2 as well as the corresponding label Y equals to Z, 0 or 1. Important thing is that Z is not observed. It's even more challenging than estimating P of Y given X with the full observations. How do we do this? We treat the latent distribution as some latent variable, of course. And then from that, we try to construct a probability of positive pair given X1 and X2. We can write it down as some factorization here, summation over all possibilities of Z1 and Z2 in this intermediate representation. And then based on each Z1 and Z2, you can measure the positive probability of positive pair. And then you can just average over the possible Zs given x1 and x2 separately. That's going to give you the probability of y1 given x1 and x2. And that's essentially the prediction that you're going to train with the binary cross entropy loss function. Yes? Yes. So do you mean the dimensionality between x1 and x2, or? So Z is a latent space with like 1,000 dimensions, and Y is a binary variable of 0 or 1. Oh, so you're not happy with using Q everywhere. It's an abusive notation in probability, like writing density functions in general. So you have to look at the variable here to kind of understand what function this is. And okay, yeah. So to be clear, one could also write down theta as a subscript here, like indicating, yeah, this is theta for Z and this is theta for Y and so on, but we omit everything like that here. Yeah, it's the same as using P everywhere, yes. Okay, yeah. I mean, in probabilities, you have to encode a lot of quantities, so yeah, there's a fine balance between being correct and being clear, so yeah, I hope it's all right. So again, we have to make this DNN friendly, as in Bayesian machine learning case. I'm gonna represent every Q here as Gaussian. We are just gonna assume, like, no one knows what the true latent looks like, but we can always say maybe it's close to a Gaussian and just plugs in Gaussian here. So in other words, I'm gonna predict mu of x and sigma of x in the latent space, and that's gonna be encoding the Gaussian distribution for each x. Okay, and now your final match probability y equals to 1 given z1 and z2, I'm going to say it has to depend directly on the distance between z1 and z2. So if the Euclidean distance is close enough, then the match probability y equals to 1 has to increase. And so I'm going to say, yeah, I'm going to put minus a here, which is a positive value. So minus a is a negative value, because you want to kind of swap, kind of reverse the relationship between distance and similarity, right? And B here to make sure that the sigma is applied in the right reflection point for the distance. Because, you know, like distance is from 0 to infinity, but now sigma is from, sigmoid is centered around 0, so you need a bit of offset here to make sure that you're in the interesting range of sigmoid for the distance. Yeah, where A and B are now trainable. So you can treat this as part of Q as well. Okay, so you can also write down A and B here as a subscript for Q, if you like. Now, you're going to turn this summation here into Monte Carlo estimation. So you're going to sample from Q of Z1 and X1 and Z2 given X2 from the distribution of this, yeah, predicted Gaussian. You know, we can do reparameterization trick again here to make sure that the parameterization and the sampling procedure are separated. So we have all the ingredients, and if you plug this in, it looks like this. It's minus slope of basically the binary cross entropy, where the eventual prediction is an average over a match probability for different samples from each of the distribution. Okay, So in diagram, it looks like this. So given x and x1 and x2, you're first going to predict mu of x1 and sigma of x1, and likewise for x2. And then you sample k1 times and sample k2 times. Yeah, you can match the number here as k. And then you're going to have k squared number of distance samples. That's quite a lot, actually. And then you're going to put minus a on top of this and plus b, then do sigmoid, and then do averaging over all k squared samples. And that's going to be your final match probability prediction. And that's you're going to put a negative log-like p-loss on top. Is there a guarantee that the true latent will be recovered using this formulation? No, because it's not a proper scoring rule for z itself. It's a proper scoring rule for y, but not for z. For it to be a proper scoring, we need an access to the samples of z, but we don't have that. So we just trust. Maybe it works, maybe not. We can only see this empirically. But actually, with a student that I'm working with in my group, we proved that for some other form of loss function for training these probabilistic embeddings, we can guarantee the recovery of the true latent under some strong conditions. It was published as an ICML paper last year. So if you're interested, I can point you to that paper as well. Unfortunately, I don't have the slide for that paper here. But you can, I can give you a pointer if you're interested. So here, kind of empirical verification is quite important. So what we used was an n-digit MNIST data set, and we corrupted the samples to introduce aleatoric uncertainty. And then we trained the 2D latent space for representing these numbers, and saw whether the clean images will have larger variances or corrupt images have larger variances. And as you can see here, corrupt images has much larger variances in general. So kind of working. For 3D space as well, we see the same pattern. For this kind of clean sample, so the squares here are class centroids. So these are not real embeddings. These are more like centroids. And this small circle here is a Gaussian distribution predicted for 0, 3. It's very clean sample, so it has a smaller variance. But for this kind of, actually 52 is a good sample here. So ground truth is 52, but you don't see the first figure almost completely. So in this case, it's because 2 is kind of clear. You see that all the centroids along the Gaussian commonly has 2 as the first digit, as the digit, second digit. But for the first digit, you have multiple possibilities like 52, 32, 22, 42, and so on. So the space is kind of working. Yeah. So summary, we have seen categorical Y and Gaussian Y, as well as more high-dimensional structural Y. And we also looked into representation learning for Z, for aleatoric uncertainty. Any questions so far? Okay. Then let's move on to the final part of uncertainty estimation, factorizing uncertainties. We've looked into different ingredients here. I write PU, EU, AU here. So we looked into predictive uncertainty, epistemic uncertainty, and aleatoric uncertainty. We briefly mentioned what these are, but we didn't actually come up with a kind of mathematical relationship, like how to quantify them in a disentangled manner and so on. So that's what we are gonna try to do here, although it's very hard to tell you the conclusion first. So for predictive uncertainty, we looked into, for example, max probability or entropy of the prediction vector for a classification problem. For epistemic uncertainty, we said, maybe you can do Bayesian model averaging and then also do max probability of entropy of that Bayesian model averaging. And that tells you how far away you are from the in-distribution samples. You can also do Gaussian mixture likelihood in the feature space to measure the distance directly in the feature space. For aleatoric uncertainty, we have seen that, we can come with a parametering module and then train it with some log likelihood to make it faithfully report the heteroscedastic noise. Okay. Why do we care about producing different types of uncertainties in the first place? So give me some motivation for doing that, right? I can give you like one application scenario in each case. Predictive uncertainty is used for example, abstained prediction. This is really needed a lot in practice when it comes to medical applications. I think I've shown some examples from there. If the machine system is not sure about the diagnosis, then it has to be able to give it to the doctor, human doctor. And that's called abstain prediction. Instead of making a prediction for unconfident samples, it simply gives up and gives it to human or some other model, or it kind of gives some kind of signal to the next stage that the prediction is not reliable, and so you have to somehow do something about it. Epistemic uncertainty is typically very useful for active learning or exploration problem, because that tells you which regions you have to further explore to gain maximal amount of knowledge with the fixed budget. Aleatoric uncertainty is used for generative prediction, for example. So in some cases, like in painting problem, for example, you do not only wish to have an estimate of how uncertain you are about the generation here, but you sometimes want to come up with different plausible answers for the problem. And for that, aleatoric uncertainty is potentially useful. Now the question is, how are they all related? Okay, we came up with different methods for coming up with this C of X for different with different uncertainty estimation methods. The question is, if we come up with C of X, is that encoding P U of X, U of X, and AU of X, maybe simultaneously, or maybe one of them, right? Or do we actually need to come up with different C of X for encoding Q of X, U of X, and AU of X separately? So there have been some prior work on trying to do that. So here's one example. Given an input X, it goes through a deep neural network, gives you some feature. So there's an intermediate feature layer. And based on this feature layer, you measure epistemic uncertainty using the Gaussian mixture model likelihood, as you have seen in lecture 10. Actually, the paper here determines the uncertainty, a simple baseline, CPR 2023. This is exactly the paper that we talked about in lecture 10. So they do that here, right? And then they also put a linear layer and softmax on top to get the probability vector for different classes. And the paper says, yeah, that value, you can trust it as the aleatoric uncertainty. Okay, and then you can probably measure entropy of the softmax output here. But now we are probably really interested in going further than just separating EU and AU, but we wish to establish the relationship in a summation way, right? PU is essentially the summation of EU and AU, right? Why do we wish to, what's behind that logic even, right? So here I can come up with some definition which kind of motivates the desire to do this. So PU of X is defined as how likely am I going to be wrong for X. But now EU of X is, you can write it down as how likely is that I'm going to get it wrong because I haven't experienced it? And then now AU of X is also how likely am I going to get it wrong, because even if I had infinite amount of experience on this, I'm not going to answer it correctly. If you look at EU and AU, these are kind of giving disjoint reasoning for why I got it wrong. And PU is encoding why I got it wrong simply, right? So that kind of gives you a summation relationship in a sense. And so conceptually, it will be very useful if there are measures, like separate measures, PU, EU, and AU for each X. That's going to faithfully represent each type of uncertainty correctly, as well as with the guarantee that, yeah, the summation relationship holds. There are some possible attempts, previous attempts for doing that. So I'm going to introduce two here. So one is using information theoretic decomposition. Here we have to assume a Bayesian machine learning framework. And here we're going to estimate a posterior Q of F. And I'm going to write down PMK for the predictive probability for model FM, which is a sample from the posterior, and class K. So it's going to be a matrix of predictions, okay? And here I'm going to define predictive uncertainty as the entropy of the Bayesian model averaging prediction, which is usual, right? You just average through through all the models, and I'm going to measure the entropy of that. Well, actually, some people say that's a measure for epistemic uncertainty as well. But here, you argue that this is a predictive uncertainty, which is also fine, right? Because otherwise, what is predictive uncertainty for Bayesian models? Eventually, you're going to use Bayesian model averaging for predicting the predictions. And essentially, the prediction, the dispersion of the prediction vector is essentially the predictive uncertainty, right? What else is? So you already see that there's a bit of problem in the overlapping definitions here and there. I'm not trying to say one of them is an answer. I'm just trying to say that there's a confusion. And it's not your confusion, that's the confusion for the whole field. So here they define P of X as the entropy of the average of PMK, right? Where average is taken among the Monte Carlo samples of the posterior, and entropy is taken along the class dimension. They define aleatoric uncertainty as something different. So they average entropy over the posterior, okay? So they look at whether each member of the posterior, each sample of the posterior is confused, okay? If every one of them is confused, then we say, yeah, actually this sample contains quite a bit of uncertainty in the output space. And so they're right, this is a really uncertain sample in terms of data uncertainty, irreducible, right? And that's basically the average of the entropy. So you take the entropy along the class axis first, and then take the average along the model's dimension. Then the question is, what is the EU then, epistemic uncertainty? To establish the identity PU equals to AU plus EU, we just define EU as the difference between PU and AU. Okay. Then by definition, we have the summation relationship. But the nice thing here is that if you define it this way, then this quantity actually has an information theoretic interpretation, which is given by the mutual information between the prediction and the model weight. To clarify the information theoretic interpretation of this quantity, I think that's one of the exercise questions. So you also take a look at that question in the exercise and try to explain what this is. But this is one nice theoretic fact. Okay. No questions so far, or okay. The second type of decomposition that people have come up with is based on risk. It's not my favorite, but you're going to see why this is not my favorite. So here we're going to use the risk and base optimal predictor. So I'm going to define P of x as the risk for my model f at input x. That's going to be my expected loss at x. Okay. So risk here means simply the expected loss value for different y for over the distribution over y. There's a big caveat. In practice, we don't have access to P of y given x, right? So in practice, if we wish to compute the value Pu of x, then we needed y in the first place. Then why do we measure the uncertainty in the first place? Because we do not have the answer. If we have the answer to the problem, then we don't need to do this complex computation of uncertainties and so on. So it's kind of a chicken and egg problem here, but how they go around this is they train a separate model for predicting this value given x. So just by looking at x, you can actually predict the risk. Okay, you train a separate model for that. It seems to work in practice, so that's why they say you can do it, but there's still a caveat. What is the aleatoric uncertainty in this case then? They define it as the minimal risk over all possible prediction on every x. So the R of x, so this is different from R of f and x, slight abuse of notation. There's a bit of overriding here. So R of x is essentially when you have minimum over different function outputs. Okay, so this is kind of the optimal possible answer that your model can give to this x, given a true distribution. And the expected loss still that you have for this case is essentially aleatoric uncertainty. Even if you can make the best possible answer here, you're still wrong because there is variance in the possible answer. Again, in practice, for obtaining this value, you need access to y. And we don't have that in many cases. So what this paper suggests is to, again, train a separate model for predicting R of x or AU of x for every x. Okay. So now, again, EU of x is now defined as the difference between Pu of x and AU of x. Okay. And that's supposed to be bigger than 0 or equal to 0 in any case, because, you know, like, R of x is essentially the minimal value of R of f and x. Okay. Yeah, so we've seen two different compositions. The question of the day is, do they actually do what they promised to do? So if you look at papers, they say, yeah, we came up with predictive uncertainty estimates. We came up with epistemic uncertainty. Or they say we came up with two different uncertainty estimates. One is encoding predictive or aleatoric. The other one is encoding epistemic. But the question is, do they actually encode these quantities? The answer is the community does not have a good understanding whether that's the case still. And with Balint, we have identified that as a very pressing question of the day for the whole community. And Balint is basically leading the research on this area. So far, the answer seems to be no, right? So even if people come with a method saying, yeah, this is an aleatoric uncertainty, it tends to correlate very well with measures for OD detection, for example, and vice versa. So we are working on that, and we will get these results published soon, hopefully. Okay, so that's it for today, and this is the feedback slide.